Swayam Prabha. Digital India. Educated India.
So here I talk about society engaged modern energy development for island and coastal community. And basically that is some philosophy or some methodology to drive convergence of wave energy converter. Basically not only engineering co-design, it's more of social science, community, and environmental science and engineers work together to achieve the system. Okay, so you already get the sense. The wave energy converter side, there's no convergence. There's so many different designs, right? You already get the sense. You need ocean engineering background, mechanical engineering background, electrical engineering background, right? And all this system together to design the system. Meanwhile, you also say you need handle environment, community, business, society, policy side. So, and however, so many different prototypes, more than one literature said they have more than 250, and another literature said there are more than 1,000 different concepts. Which one is best? You may say, Professor, what do you mean which one is the best? What is the criterion to judge which is best? Okay, so there's one paper studied by Professor Branny Dupont, okay, and she published a paper. Actually, this is undergraduate senior design work, but they did a nice survey, collect all the opinion. Here, about I think more than 30 companies feedback to say which one is the best. Okay, so here it shows that one, and among these 11 companies say I use RSOE, donors per kilowatt, to judge which one is best. Okay, so you already learned the RSOE, capital cost, operation maintenance cost divided by the total energy, right? So that is the RSOE. Look at the other company, okay, and there's a technology readiness level, right? 4 companies, they use technology readiness level. 3 companies, they use technology performance level, right? And one company said, okay, this is uniqueness, right? Customer metrics, and another sense, and they said, okay, I will use government's metrics, whatever set up. So you get a sense, okay, this company's feedback survey and not uniform, right? RSOE is most popular one, but RSOE is very complicated. You need to consider the cost of the system in one life cycle. What I mean, you design 20 years, you have to consider all the things in 20 years at the design phase predict. There are a lot of uncertainty, right? A lot of things, environment and policy, all the type of things hard to use. Okay, and so another thing, technology readiness level, right? This is second popular thing, technology readiness level. And what technology readiness level, right? The basic technology research 1 to 2, and you prove the feasibility and do technology development, technology demonstration, eventually you launch the product, right? Technology readiness level, and there's nice thing, right? So how quick you can commercialize, you feel, wow, it's ready, right? However, one important part is missing, cost, right? You say my system is ready to put in the water, whatever like that, you don't know the cost. And another thing, you don't know the performance. Yeah, my technology readiness level high, but how much power you can get at what kind of cost, right? You don't know. So this is technology readiness level. And a third index is technology performance level. technology performance level is proposed by Weber when he was in Bob in Ireland. And now he's chief engineer at NREL. He pushed that for about 20 years about technology readiness level. I like the figure he gave to here. Okay, take a look at the figure. Technology readiness level and technology performance level, right? And then this corresponding to technology development cost and dollars per kilowatts. Okay, or in his he write a serious paper to push forward in this direction. So mostly, so we have one concept. We push to here to put the tank test, right? And you get technology readiness for file. Meanwhile, you push this direction. However, the performance may not be very good. Eventually, you push things in the tank in the open water test, right? That performance is still not good enough. So sometimes you start reset, right? You find some concept with high technology performance level. It has a good performance, and then gradually increase slowly on the technology readiness level. Here you push very fast in the technology readiness level, but the performance didn't improve much. Here you didn't drive technology readiness level much, but you quickly improve the performance, eventually achieve the high RSOE, right? So at good performance. He developed very systematic way to evaluate technology performance level from 1 to 9, and so far it's still too complicated to become popular, right? As I mentioned, that his nice work he pushed 20 years, but it's still there, not adopted. So what I mean, I want to give impression to you, and we don't know which one is best. There's no widely recognized criterion to say which one is best. So how you draw the research convergency? So, and there's some format change, okay. And another thing is social environment side. And technology readiness level, they didn't consider social environment. Technology performance level considered somehow, but not that obviously, all right? So you need to consider the regulation, the legislation, the social acceptance, and the environment impact, right? So talk about environmental impact, I have to show this figure, okay? And that is okay, here, this figure is taken from Dr. Andrew Corbin's lecture notes, as well as the state of art report. Okay, so this figure shows what kind of stress receptor interaction. Let me change this part a little bit. So now, environment of marine renewable energy, right? I take this slides from Dr. Andrew Corbin at the PNNL's National Lab. So here they talk about what kind of environment the marine energy will have, and it talk about collision risk. Basically, you have cable like that, or you have structure, wind turbine, or no water turbine as marine structure, wave energy converter, the memo will get cut, right? This collision risk. And also underwater noise. You have turbine system, right? And you have wave energy converter, it generates noise, right? Or you have wind energy side, wind energy, you draw that, there's noise, right? Then you have electric field, right? All this cable, whatever, you have electric field. This may have influence to the marine mammal. And then you may change the habitat, this type of environment, right? And marine line, this type of thing, we get tangled with fish wear different system like that, right? And you may change the oceanographic system, for example, the sand the accumulate here, right? And you may push them some fish mitigation trajectory away, right? So that is impact. So the important part in this conclusion, so this is published in 2020 or 2024 and by is International OES Environment Report. Okay, so and State of Science Report here it highlight all the environment impact is many countries study together that publish that. Most of the environment impact retailed. What I mean is minor, is not a big deal. So I highlight 3 parts that this area need to considered according to this report. One is the collision, right? And like the turbine, whatever like that, this collision with marine mammal. Another noise, specifically, this give one example of noise. If you install anything like that, and no matter wind energy, wave energy, you may have some pairs. When you draw these pairs, and it generates a huge noise. This noise can kill all the marine mammal kilometer away, right? So that is, so noise impact. And this figure shows noise impact. Outside the noise, you put a bubble here, bubble go up, then bubble curtain reduce the noise. We have new project funded by DOE how to get a result better than bubble. Okay, we call the metal material, and we get energy noise reduction in the primary pass and also in the secondary pass. We use so-called metal material. Okay, so noise is still there, collision is there, displacement. Basically, you have a wind energy or wave energy farm, and if every year this whale or dolphin go through this one, they try to avoid this area, right? This is called displacement impact. So this is environment impact which we should consider. Okay, and now I want to say the community side. Here we highlight community-centered core design concept. This is actually one project we studied at Michigan. So the background, there's one island here. This is Michigan Island. Okay, this is island in Lake Michigan. Okay, so Michigan, this is very large. This okay, and from, for example, from here to drive to here, it takes long hours drive. Okay, so you get sense how large Michigan is. Okay, so University of Michigan is here. This is Lake Michigan. This is Lake Huron. This is Lake Huron, Lake Superior, and Lake Erie. Okay, so this is the largest island in Lake Michigan, second largest in the Great Lakes. Okay, there are 600 residents, and summertime it can be 2 times or even more, 1,500 people who live in the summer. Okay, winter time, year-round residence is 600. So such kind of island, they count one underwater cable to provide power. Okay, basically this place is 27 miles, 43 miles away. The cable go under the water. Okay, in 1999, for whatever reason, this cable get cut. So you can imagine that way, Michigan is very cold. And winter time, there's no electricity, right? It's a problem for them, and it takes them a lot of effort to recover. In that time, they get a backup diesel engine to power the system, but it takes time for them to install. Okay, so the resilience of this island community is very important, right? We want to increase the energy equality and sustainability of this island using the wave energy converter. So one common mistake all the engineers, okay, or most engineers are making, okay. So we think they need this. Therefore, we create something, we build something, we try to convince the end user, oh, we develop wave energy converter, we can give to you with the minimum cost, even free, right? Engineers want to create a system, convince other people to use, right? This is a mistake, right? And instead of we create a system, ask them to use, we need to consider what they need, right? We know what they need electricity. The question is what they want. What kind of constraint they have, right? We need to, engineers need to team up with the social scientists and with the community to get the work done. Basically, the outline is we engage the community, right? And we look into what they need, what kind of resource on the island, right? After that, we engineers come up the technology concept. Then we get engage with the community again, do this iteration, right? And let the community participate in the design on day one, right? Not engineers come up with the conclusion, build the system, and give to them after we build that, right? We want the community participate in from day one, right? After we go through this concept, then we finalize the design. We do some this assessment of this community. We look into permission, all the type of thing. Eventually, we deploy a test system together with the community. Is this clear, right? So engineering co-design is not enough. We need to get community together, get social scientists together to do the design work. So this one, we get small grant for Michigan and middle size also from Michigan with different collaborators, and is ongoing work. And based on that, so, okay, we develop a very large program. Okay, so before we talk about that large program, I want to show you the community engagement and the environmental resource we have. Okay, so for this lake side, this lake is large and its wave energy typically is 3 to 5 kilowatts per meter, right? So compared with the ocean, it's more like half ocean. Half ocean, what does it mean? We learned from scaling law, right? Half ocean means the amplitude, the wave amplitude is half, and wave period is square root half, 0.7, right? Times the ocean wave period. If ocean wave, let us say 8 seconds in the lake, half means 5.6 seconds, right? Then amplitude, if in the ocean 1.5, that's 0.75, okay. And how about power? Power is scalable, is about half, is about 11%, factor of 10. Okay, anyway, so you say in the ocean east coast, you can get 20 kilowatts, west coast 40 kilowatts per meter. So that's why here is 3 to 4 kilowatts per meter. 3 to 2 kilowatts is not a small number. You remember the map I show you in the Indian, this region, and it's more like the number. In South Korea, it's more like the number. The China South Sea close to Hong Kong, the place is that power number. Okay, so and in the past, we went to the island multiple times, and we have a lot of engagement with the community. Okay, so we are in the process to develop such kind of wave energy converter for this island's application. We are not ready to power whole island yet, and however, we want to give some smaller scale demonstration. For example, such kind of wave energy converter probably can power the environment monitoring of the ocean, right? Lake, not ocean. Anyway, you stay here, you wouldn't be able to tell this ocean or lake. You cannot see on the other side. Okay, so, and it may be used to build a navigate mark. And every day there are two to three ferry ship from here to here, right? and there are other fishery or kind of activities here. So we are still in the process to identify the need and identify the market yet. Okay. Based on such kind of initial work with this island community, we write a larger proposal to NSF, and in this one we get $3.6 million for 5 years this project. Yeah.
Sir, we are getting wave energy from lake. How big is that lake then? It's a very...
How what?
If we are getting wave energy from lake, like how big is that lake? It's very, very large, I think.
Let me say, you are getting energy from lake. Your question, how large is the wave in the lake? Yes.
Yeah, because the fetch and all these things need to be big for the
Okay.
wave to...
Let me tell you, from here to here, you drive here, and let me say, from here to here, we drive 4 hours. So you get sense what the fetch distance, right? And in US it's highway. We normally drive 100 kilometers per hour. So if you look at the fetch distance from here, probably 400 kilometers. Right, it's pretty far. And the wave is not small. And this one shows the wave in terms of kilowatts per meter. Okay, so for example, in winter time, and the south side of the lake, you can get 9 kilowatts, 7 kilowatts per meter, right? North side, you can have winter time, you can have 6 to 7 kilowatts per meter. And summertime overall is small, like 1 kilowatt per kilometer, per meter of width, right? So average, you may have 3 to 4 kilowatts per meter. You build one device, average, you generate, let us say you get 10% out, then will be 3 to 400 kilowatts. 3 to 400 watts, you times 10%, right? We don't know that yet. Most of the small devices capture overall wear to efficiency is less than 10%. So, however, you still can get 100 watt sense that can power the environment monitoring, power the navigation mark. Is this clear? Okay, thank you for asking. This gave me a chance to clarify what this figure about. So, that is different season, how much power we can get. This Green Lakes is half sea. Okay, yeah. More question?
Sir, in the case of taking average, like, is it okay to take average per year or per season? Like, that will be more accurate.
Okay, and depend on what kind of thing you use. Actually, one thing I didn't mention that, okay, and then let us say, I say why it depends on what kind of thing you use. Okay, you wanted to power the ocean monitoring system, right? Probably is not even average per month. Probably is average 1 week or 2 weeks, right? You harvest energy, you power the ocean monitoring system. You need to prepare that. Okay, you store everything in the battery, right? When these days there's no wave come, the buoys still get enough power or not. In that sense, how much your battery can last, that is the average you need to consider. Make sense? Right? So if your battery can only last 2 weeks, this small size battery, you need to consider the average of 2 weeks, right? So another thing I didn't mention that Green Lakes is fresh water. In fresh water, what happens? Ice, right? Winter time, it covered with ice. It covered with snow. What you will do? We are looking for some solution, and actually, it's hybrid system which combine wave and small wind, or even sonar. And this community is very conservative. So for such kind of community with 600 year-round residents, you would think it's good enough to put a 3 megawatt turbine there. The community, they don't like turbine. No, not as view. They don't like turbine damages the vision, right? The community is not that large. You put a turbine there, someone will say that from the backyard. People always say, hey, yeah, I like renewable energy, I like wind energy, but not in my backyard. Make sense? Where you put it in the ocean or lake, people cannot say visibility is not, the impact is not that large, right? The important part that is engineers need to know, you think, wow, 3 megawatts wind turbine is good. I can help you to get state funding, to get government funding. I install 3 megawatts wind turbine for you for free. The community wouldn't like. And this community is underserved community. However, this community are pretty rich. The house is very expensive compared with an arbor. The reason is, you just imagine that way, that is a very nice vacation area. This is why summertime, the year-round residents 600, summertime can double, even increase 3 times. Because a lot of people, they buy the house, they live in the summer, right? And these are rich people, just in the beach area. You like around here, the beach house is more expensive. Here is beach house. Make sense? And this house is better than Florida place. Why? Florida year-round the storm come and get your water into the house. This is a lake, and there will be storm, but that is not dangerous, right? So it's underserved, but also rich community. Therefore, the opinion, they said, we don't want to lose our property value. I don't want to, from my window, I saw this wind turbine, right? So the community opinion is important. You not only consider what they need, you need to consider what they want also. They need electricity. You think 3 megawatts wind turbine is good enough for your community. You don't want. Make sense? Okay. So based on that, we write another proposal, right? Is the title is Power Remote Coastal Community and use sustainable wave energy converter. Okay. So what does that mean? Okay. And is previously is preliminary work, right? We extended this preliminary work. We want to drive the research convergence with wave energy, right? With considering environment, society, community, and engineering together. Okay, so I mentioned that there's no research convergence, right? There's no research convergence. We don't know which one is the best. We want to build a framework to drive the research convergence. This framework includes 3 parts. One is drug discovery inspired market pull approach, and also 3-dimension technology, environmental, society assessment, and we engage the community side. And we have 2 phases. And first phase is to build the convergence roadmap in the first 2 years. Then, rest of 3 years, we are going to conduct a system level co-design, also community validation. So with this one shows Beaver Island, and we also engage other community like Outbank, North Carolina, and Florida, Key West, and Alaska, Hawaii, such kind of remote community. Okay, so first I say the drug discovery inspired design. So let us say that way. I know India is pretty good in drug development side or manufacturing side, and drug discovery. Okay, I take one example. Pandemic, COVID happened, right? So what the people have done is identify some protein and that associate this related with such kind of virus, right? Then I look into what kind of components can kill such kind of virus, right? So engineering in another side, for example, you have one idea, you have one technology, right? Then you want to drive the technology to the market. It's technology driven, right? I have one core idea. I want to use this idea to develop wave energy converter. That is in your mind. This is technology driven. Drug discovery is another side. I don't know which molecule can become drug, right? Not on chemistry, I invent a molecule, yeah, I want to make a drug. It's not like that. I have a need. There's a disease there. I need to take care of the disease. I need to look at all the possibility, all kind of molecule like that, right? I identify something that can potentially interact this type of specific protein that's like that. We call that is hit, right? Hit, what does it mean? You have some target, you hit that. This is called hit, right? And after you know this can have interaction with this, then it may become drug. If there's a molecule that has nothing interact with the specific target, it can never become drug, right? So we put it outside. And for the hit, when we go through the optimization process, this need, right? So usually you start with millions of compounds. You get 1,000 of hit, right? Go to high throughput screening process. After that, you take 100 or dozens of compounds to do the optimization process. Eventually, you select some compound like it's called preclinic trial study. In this type of case, you may use pig, right? You may use monkey to do such kind of preclinical study, right? Eventually, only one or two go through the clinical trial, right? Clinical trial is a very, very time-consuming, resource-consuming process. Okay, so that is what I learned. 4 years experience in the company. I have pharmaceutical company 4 years experience. So I get a sense of what they are doing. Now, I'm in the ocean engineering department, naval architecture and marine engineering. I drive the research convergence using drug discovery inspired process. Instead of I invent one technology, I put it in the market. I want to identify what the niche market first. And instead of technology driven, I have market pull and technology driven process. The idea is like that, okay? And we identify the remote community as our target to work on, right? Then we develop the framework, how to narrow down the concept. We look into all the possibility of the concept that will help the community to achieve our goal. Then we narrow down several concepts. Then we do lab study. Lab study is more like the tank study, a tank test corresponding to preclinical study, use monkey, use pig to trial, right? It costs, but is compared with clinic using human being to try this one, it costs less, right? Eventually, I put this into ocean. It's more like clinical trial, test year round like that. So this is drug discovery inspired wave energy convergence. We need to consider the fluid structure interaction, control electric, and PTO design, this type of thing in this framework when we talk about core design. So, and another thing is about technology economical assessment, right? We say technology readiness level 1 dimension, and we have another dimension, social environment acceptance. This is one dimension. Then we have economic side, donors per kilowatts, and here we adopt one idea that proposed by Upper E director Moria, and in the SHARKS program, he used kilowatts per kilogram was index that is more convenient than donors per kilowatt to evaluate the economic performance. So this framework is still in the process development. Basically, we want to develop the framework together with the community and end user to draw the research convergence. For example, if you have multiple concepts, reference model 5, reference model 3, reference model 6, right? You put such kind of performance index in the space, 3-dimension space. You want to drive the research convergence, achieve the good economic feasibility, good society acceptance, good technology readiness level. This third approach is community engaged co-design, right? And the leadership team will engage with community. We form community council, advisor board. We work with students and international research or leader research in the field, right? We engage everyone, right? And from the concept phase, community engagement, we do iteration, consider community's opinion at each phase, right? We also have scientific way, and by collaboration with social scientists, how to evaluate the environment society impact. So, and I show you the team first. So in this project, I'm the PI, and we have Jeff Scruggs, my colleague, work on the control side, and we have Professor Daniel Tefti at Virginia Tech, my former colleague, and work on the hydrodynamic study side. And we have environmental scientist Lindsay, and we have social scientist Eric, and work on the environment and social science side. And we have Dr. Daniel Dunn. He is an adjunct professor at University of Michigan and a research fellow, lab fellow at PNL to do the bioenvironment study side. And we form and community council, and with Gear in the B1 and as co-chair, we have Bill Stebby and in industry to chair the external advisor committee together. So it's 5 years progress, and we started recently 3 months ago, right? And we identified the target, and we developed a convergence roadmap. Then we take a drug discovery inspired approach to screen all kind of concepts. Then we are going to do co-design, co-optimization, lab validation of several leading concepts. Then we are conduct field test. Okay, this field test, it can be in the Beaver Island, it can be in North Carolina, this type of community. Okay, so, and if you look into University of Michigan's website, I don't know if today is still there or not, and in the past week it's still there, and it highlight our work about community-centered wave energy converter design. Okay, so now, wait a second. Before I conclude this page, I want to say your guys' opinion.